In this video, we're going to talk about how to solve a linear programming problem using the graphical solution method, which is a method typically used to solve problems where there's only two decision variables. Let's take a look at this example here. We have a company that produces specialty golden plates and spoons, and each gold plate takes 1 hour to make and requires 4 ounces of gold, whereas each golden spoon takes 2 hours to make and requires 3 ounces of gold. The company has a total of 40 hours of labor and 120 ounces of gold available. Each plate yields a $4 profit and each spoon yields a $5 profit. And they want to know what combination of plates and spoons should be produced in order to maximize their profit. The first step of this problem is to define the decision variables. And here we must decide how many plates and spoons we should produce, which will give us the highest amount of profit. So I'll let x1 be the number of plates we produce, and x2 be the number of spoons. Now we can start to write the model for our problem, and we start by writing the objective function in which we try to maximize our profit, which I call z, and our profit is determined by adding the profit from the plates, which will be $4, times the number of plates we produce, which is x1, plus $5 times the number of spoons we produce. Now we can start writing the constraints for our problem, and these constraints will help us to use the resources as efficiently as possible. One of the constraints is for labor. We have 40 hours of labor available, and each gold plate takes 1 hour to make, whereas each spoon will take 2 hours. So we can write that here as 1 hour times x1, the number of plates we produce, plus 2 hours times x2 has to be less than or equal to 40 because we can't exceed the number of hours that we have available. Similarly, for the other constraint we have for gold, we require the plate to have 4 ounces of gold and the spoon to have 3 ounces. And in total, this can't exceed 120 ounces of gold. Our last constraint is somewhat implied. It's called the non-negativity constraint, and it's just so we make sure that we don't produce a negative amount of plates or spoons, which wouldn't make sense anyways. So we'll let x1 and x2 be greater than or equal to 0. Now that we have our model and constraints set up, we can start plotting these constraints, and we'll get a feasible region, and using that we can sort of find the optimal solution to this problem. So let's take the first constraint here. We can plot it just like we would any regular line. So we'll take 2 points on this line. Let's say if we have x1 equal to 0, then 2x2 would be equal to 40. We'll assume this is a line for now and then take care of the inequality later. So then x2 would equal 20, and our first point will be 0, 20. And so let me just label the axes here. We have x1, which is typically our x-axis, and x2, which is our y-axis, typically our y-axis. And let's label the point. So we'll label our point here 0, 20. And we can find another point on this line. If we take x2 equal to 0, then x1 will equal 40. So the other point we have is 40, comma 0. And again, let's label our axis here. So 40, comma 0 is the other point on this line. And we can connect these dots to get our first constraint. So for the second constraint, we can follow a similar process, and I'll just write the points here that I'll use to plot. So we'll have 30, comma 0 and 0, comma 40, and let's just plot these. 30, 0 and 0, 40, and we'll connect the dots. This will be our second constraint. And lastly, we can plot our last constraints, the non-negativity constraints. These are just the axes themselves. So x1 and x2 greater than or equal to 0. So that just means that our answer has to lie within the first quadrant. So now we have to take care of our inequalities in the constraints. And since our first two constraints have a less than or equal to sign, we know that the solution or the feasible solutions must lie below these two lines. And so I'll shade in the region here that corresponds to the set of all feasible solutions. So this satisfies all the conditions we have, and we can find the boundary points that help to define this region. So one of the corner points is here at 0, 0, which I'll write as point A. Another boundary point is at 0, 20, or point B. Another lies here at the intersection of the red and blue line. I'll call it point C. And then another lies at 30, 0, or point D. To solve this problem, we have to plug in each of these boundary or corner points into the objective function and see which point gives us the highest value. Starting with point A, which is at 0, 0, where x1 equals 0 and x2 equals 0. If we plug this into Z, we'll get 4 times 0 plus 5 times 0, which is just 0. And we can continue with each of the points similarly. So we have our next point, which is B, that occurs at 0, 20. So for that, Z equals 0 plus 5 times 20, which is 100. So point C, it takes a little bit more work to find the exact point, but if you solve the equations for the red and blue line, you'll get that point C occurs at 24, 8, and so Z equals 4 times 24 plus 5 times 8, which gives 136. And lastly, we check point D, which is at 30, 0. And so Z is 4 times 30 plus 0, which gives 120. Now, since this is a max problem, we choose the highest value among all our candidates, which is 136. And this represents our maximum profit. And this occurs when we produce 24 of x1, which, if you remember, is the number of plates we choose to produce. And if we produce 8 of x2, which are our spoons.